Hey guys, hopefully you saw the last three videos on elementary flows, stream function, Laplace equation, and potential functions. In this video, we're going to talk about the homework, just your next homework on elementary flows. Um, so let's get to it. You can actually find the handout for this homework attached along with the series of videos and guided notes. Right? So question one asks you to determine, basically simulate flow over full ranking. So as we discussed in the last two or three videos, um, to create a flow over a full ranking, you need to superimpose uniform flow, source flow, and a sink flow. So basically, this is the equation you'll be programming, right? So, but please make sure to basically code the x naught and y naught in the program because that's a location where you place the source and the sink. Again, given a Cartesian space, you can place them anywhere you want. It'll be easier if you place them on the same plane, or in other words, same axis. Like you can keep the y-axis the same. Otherwise, you can simulate flow over the full ranking at different angles. So to keep it simple, if you keep the y-axis the same, which is basically y naught 1, y naught 2, and change the x-axis, basically you're placing them on two different x locations, but on the same y-axis, may make it easier. Okay, so that's an equation you're programming. So what is asked? So you should plot the stream function contour. You can do that using the contour f function. So in the first video, when I plotted the streamlines, when we talked about the stream function, I gave you an example code that kind of shows you how to plot the stream function contours so that you can actually see the streamlines. So just go and take a look at the code and use the same formatting. Makes it easier to actually visualize, right? So again, you're looking at psi xy. So that means in order to do this, you need a mesh grid, right? You need to create a mesh grid of x. You need to create a mesh grid of y. You can control the range. Again, it's just up to you. Just don't make it like -100 to 100. If you make it around -10 to 10, -5 to 5, that's pretty pretty simple, right? So once you have the stream function, you can find the velocity vectors around the cylinder. Again, we talked about how we can do that, right? So in order to find the velocity vectors, you differentiate the stream function with respect to x and y. So ux dou psi by dou y and v is minus dou psi by dou x. That'll give you the x and y location, right? So given the stream function, you just do a symbolic differentiation in MATLAB, and you will get an expression for u and y, u and v in terms of x and y. And then all you got to do is use quiver command to plot, x, y, u, v, so that you can actually see the vector field. All right. Now I got a caution that so if we go back and look at the stream function equation, at some point, if your denominator, which is basically x by x minus x naught 1 and x minus x naught 2, when they go to 0, these values are going to go to infinity, right? And MATLAB doesn't really like that. It'll do its thing, but when it comes to plotting the velocity vectors, when these denominators go to 0, your velocity vectors magnitude is going to shoot up by a lot. So you may have to manually remove high magnitude velocity vectors, right? So just check, if your velocity magnitude is in the order of 10 power, 5 or 10 power 10, you know that that's not right, right? So just go ahead and remove those manually so that you can see the rest of the vectors pretty clearly, okay? Again, guys, this is important, right? Don't ignore this step. Um, this is crucial for you to see the velocity vectors, right? So once you plot the velocity vectors, you got to identify the stagnation points, and you got to show or highlight the surface streamline, right? So in the last video, or the couple of videos, we talked about how we can do that, right? If you want to know the stagnation point, all you got to do is set u and v equals 0, and you solve for x and y. So you can use the MATLAB solve command um, to basically find the x and y location. If you want to do it by hand and check if you get the right answer, So you can set y-axis as 0, right? So that you place the source and sink in y equals 0 line, which is the x-axis, right? So you at least know one location on stagnation point, and you just have to find the x-axis location stagnation point, right? So once you find the stagnation point, you need to find the surface streamline. And the way you do that is, you substitute this the x and y axis stagnation point locations to the stream function, right? So then you will actually find the stream function associated with the surface streamline. So once you know that value, that magnitude of the surface streamline, then you can ask MATLAB to basically highlight that, right? So there are ways you can do that so that you can actually see it. So the next is, coefficient of pressure and velocity variations. Um, this is what I was talking about. You can actually see the source. So this is where my source is. This is where my sink is. As you can see, velocity vectors closer to the source and sink, because the denominator goes to 0, the vectors will have really, really high magnitude. So you really need to make sure to manually set them equal to a NaN variable, or or basically go to 0, right? Once you do that, the other vectors becomes reasonably visible, right? So again, you find the stagnation point right here. You'll get an expression, analytical expression for the location of stagnation point. Just make sure to check if those agree with what you see in the graph right here. Okay. Once you find that, then you can pretty much set everything that is inside that circle or inside that surface streamline as 0. So, but that doesn't really interact with the flow going outside. So, right, and basically that's what you get, right? Now, if you want to find the coefficient of pressure variation across the surface, so and all we're asking is to see how the velocity varies and the pressure varies along the surface, right? So in order to do that, first things first, you need the x and y locations of the Rankine surface, right? So that means in MATLAB, you know the value of the streamline, and you can ask MATLAB to basically find the coordinates that has the same value of stream function, okay? Again, you gotta, you can figure out how to do that. There's a nice command in MATLAB called find. So it's you can use, that's just one of the options that you can use, right? So once you find the x and y locations of the Rankine surface, then you plug that into u and v velocity vectors. Then you get the u and v velocity along the Rankine surface, right? Now, the quotient of pressure variation, and you guys know the formula, right? Cp is 1 minus V local times V infinity square. In terms of U and V, it's basically into magnitude, right? So square root of U squared plus V squared. So once you find that, you can basically plot Cp variation as a function of, x-axis or y-axis. So, just plot Cp as a function of, like, say, the chord length, right? And watch what happens. So you should get an intuitive understanding of how this CP should change, as we talked about. In the stagnation point, the CP will start at 1. As the flow goes around the curvature, it accelerates, and it accelerates more than the free stream. So it should go negative and then come back to again the stagnation point, which is about 1, right? So you should get a velocity CP variation of something like this. So if you get any other shape, you know that there is something wrong in your code, right? So that's pretty much the first problem. Again, it's all getting used to how you can get the velocity and pressure information just from addition of stream functions, right? So the next question, question 2, asks you to plot or simulate flow around a cylinder. So similar to what you did in the Rankine, flow around a cylinder, you're adding the uniform flow, and then you're adding the stream function for the doublet flow, right? And again, make sure to keep the x naught and y naughts in there so that you can control the location at which you keep these the location of the doublet, right? So this is the stream function you're coding, and you basically go through the same steps to actually find the stream function contour, the velocity vectors. You still have to remove some of the high magnitude velocity vectors. And for this, you can assume velocity value of like free stream velocity 1 meters per second and a doublet strength of 300 meter cube per second. But I just stated here so that you have some value to work with. But really, this value depends on your x and y range. Okay, so I believe my x and y range for this was between negative 30 to 30. But if you keep a different x-axis and y-axis range, then you may have to change this value so that you get the cylinder within the field of view that you're looking at. Okay. Again, don't confine yourself to just 1 meters per second velocity. Just change the velocity, free stream velocity, and see what happens. You're developing this code anyway, so might as well play with it, right? So, and similarly, what a lot of sort of how we discussed before, you find the velocity and CP distribution, right? You're following the same steps as you did in question 1 for this question 2. Okay. All right. So then the third question asks for you to plot the flow around a lifting cylinder. And now in this case, you're adding uniform flow plus doublet flow plus the vortex flow right there, right? And this is the stream function that you're adding to the cylinder, right? Again, make sure to use the normalized radius in the vortex flow stream function equation. And you guys know that this radius is a function of kappa, right? So don't set radius equals 1. You won't get the right answer, okay? At the radius, we got to make sure the stream function value matches that of the stream function value on the surface of the cylinder using this doublet and the free stream, right? So that's the main reason why we normalized it, right? So program this equation. Then again, you're basically going through the same steps to get the stream function contour, velocity vectors. Now the velocity vectors are gonna get pretty long because it's a pretty big equation. That's why don't even try doing this by hand. Just code it in MATLAB and get the U and V equations. Okay. And then you're basically plotting. The only thing that will change is you need to add a vortex strength as well, like circulation. So basically, these are all the different things that you got to do to simulate flow over a lifting cylinder. Again, keep in mind you still have to remove the high magnitude velocity vectors so that the vectors are basically visible. Okay, so you go through the same process to get the velocity and pressure distribution as well. Once you find the stagnation point and then the surface streamline, plug that into the velocity equation, or plug that in the stream function to get the surface streamline, and then plug in the surface coordinates of u and v into the velocity equation, and from there you get the CP. We even talked about this when a couple of videos ago, right, on how you can actually do that, right? So one more thing that you can do on the third question is basically look at how the flow field changes for different values of circulation. Remember, we came across this plot right there. So as you increase the gamma value, you have two stagnation points, and then as the gamma keeps increasing, the stagnation points moves closer and closer to the bottom surface. At some point, it's going to come off of the surface, right? So you're trying to find, create these different flow fields, using your code and try to understand, how things, change. Okay. Again, I should caution here is that since you're looking at an asymmetric flow field, be very careful in determining the velocity and the CP variation because it's not going to be the same as the cylinder. Okay, because you will have an asymmetric velocity distribution. Okay, all right. So, and the last question, which pretty much ask you to generate flow around a shape of your own choice. So that means that if you want to simulate flow over something that looks like an airfoil or something that looks like this type of shape, pick an object that you were interested in. Maybe like a golf driver, right, or a golf. You already simulated cylinder and Rankine, so just pick a little bit more of an asymmetric shape so that you can just have fun playing around with these elementary flows. So no matter what, another interesting thing that you can do is you can try simulating cylinders or cylinders with rotation at close proximity to each other. Um, that kind of gives you a very interesting flow field. So these are just some ideas for you to look at, but you don't necessarily have to do this. But just come up with your own flow field that you want to simulate, right? So in that, you are basically you can figure out the stream function contour with the surface streamline highlighted. So again, remember, no matter what object that you're trying to simulate flow over, you got to solve for the stagnation point, and then you got to find the streamline that's going through that point, right? And velocity vectors using the quiver command. So you differentiate the stream function, and then you solve for u and v, and then you plot them. And surface velocity distribution. Basically, you plug in the x and y coordinates of the surface in u and v velocity vector equation and get the surface velocity. From there, you can actually get the CP distribution, right? And then, if your body is asymmetric, you can actually find the forces that are acting on that body, right? Which is very important, right? I mean, this is what we've been waiting for since the beginning of the class, right? This is the first way that we were able to simulate flow over complex shape objects and determine the velocity and pressure variation around the object. Even for an inviscid case, this is still pretty cool. And it's a very important skill to have. And remember that all of these concepts were developed back in like what 1788 and 1789 when even the computers were not developed. So if they can do it back 200 years ago, we can now as well. Okay, so that's pretty much the end of the series, the video series. Um, so I hope you really understood the value and the significance of the stream function, potential function, Laplace equation, and elementary flows. And it allows us to do some really, really cool stuff. And I hope you have fun doing this homework. All right.